So the Bitcoin SV technical update is normally about the current state of the Bitcoin SV infrastructure and ecosystem in general. But today, I want to talk about the future instead of today. But it does begin in the past. A long time ago, in a forum far, far away, a gentleman by the name of Satoshi Nakamoto gave us a glimpse of what the future of the Bitcoin network would look like. At equilibrium size, many nodes will be server farms with 1 or 2 network nodes that feed the rest of the farm over a LAN. Here, Satoshi is describing not only a Bitcoin node running across a large cluster of servers, but also the specialization of different parts of that cluster. So today, we're going to talk about the realization of that vision. To fulfill that vision, we need a system that can process millions, even billions of transactions per second. And that requires a shift in paradigm. It requires a shift in the architecture of the Bitcoin software. So today, we're going to see, for the first time, a sneak peek under the covers of the Teranode Open Framework. Now, I will stress that Teranode is a huge subject. We're not going to be able to even scratch the surface today. I want to explain the structure of the project and some of the kind of key properties of the project. And then we'll take a look under the covers. So the first step in building an engine like this is before you build the thing, you need to understand what the thing needs to do. And that's the requirements. And of course, the first one is a high scaling factor. If we want Bitcoin to be unlimited, then we need to be able to scale it with no limit. So we talk about the capacity of the Bitcoin network right now in terms of numbers of transactions per second that it can handle. That is going to become an irrelevant metric because it's intended to be a function of how many resources are actually thrown at the infrastructure of the network. And that in itself is a function of the amount of revenue that is available to miners. So Bitcoin is designed in a really nice way because the more demand there is, the more revenue available, and the more infrastructure is available then to supply and satisfy that demand. Another key requirement is that we need to be able to process and propagate transactions within 100 milliseconds. One of the key features of Bitcoin, one of the key problems that it solves, is the ability to achieve transaction finality in a very short space of time. That means that a transaction has been distributed and accepted by all miners on the network, and our goal is within 500 milliseconds. That means 500 milliseconds after you send your transaction, you can be assured that it will not be double spent. You can be assured that it is final. You can be assured that it is a real payment. And the last part that we really wanted to focus on was incentivizing a competitive ecosystem where miners actually compete with each other to improve their efficiency and improve their capacity. And of course, the last one is don't break Bitcoin. Now, Satoshi actually had something to say about multiple implementations of the Bitcoin node. And in fact, this argument got brought up and thrown in my face quite a few years ago when I got into an argument with Mike Hearn because I wanted to turn Bitcoin J into a node implementation. But it's key that we need to be careful in the transition because Bitcoin software is really just a collection of well-known computer science problems solved in interesting ways that are not actually that unusual. But it does have one unique property, which is its consensus mechanism. And that presents risks when you're trying to make 2 versions of nodes incompatible. You can end up with 2 nodes that actually have a different view on whether blocks or transactions are valid. So we've got a very careful plan to roll out Teranode to assure that we don't cause breakages in the process. But first, let's talk about scaling and the concept of a scaling factor. The way that the existing Bitcoin software is architected, it's monolithic. It's designed to only run on one single machine. That means the only way that you can increase the capacity is by increasing the size of the physical machine. But of course, there's a limit to that. So we can scale up, but there is still a ceiling. We've done a lot of work in the Bitcoin SV software itself over the last 3 years to ensure that it can actually vertically scale because the original software that we inherited from BTC was actually single-threaded, so you couldn't even scale up in this way. But the way that most of the world does scaling the Googles, the Facebooks of the world, the largest data centers, the largest data processors in the world, is horizontal scaling. And that's simply scaling by being able to spread workload across multiple machines. And the idea is that you continue adding cluster nodes as you need more and more capacity. And if you have a scaling factor close to 100%, this is a really efficient way to be able to manage any kind of a workload. The scaling factor is essentially a metric that we use to measure how well a system actually can scale. That is, if I double the number of machines, I should ideally get double the amount of throughput and working capacity. Rarely do you achieve perfect 100% scaling. Usually at 90, 95% is a great target to aim for. So the Teranode project is built in a number of modules. The framework itself is the basis of everything. It's actually completely agnostic to Bitcoin. It doesn't know about Bitcoin. In fact, it could be used to scale any type of workload. It just happens to be built in a way that is very complementary to Bitcoin's design. Components know nothing about the framework. They actually just implement bits of Bitcoin logic. And the components can actually be used outside of the framework. And pipelines are what tie it all together. A pipeline is basically a sequence of tasks that need to be performed in order to complete a larger job. An example of this is validating a new transaction that comes in. And pipelines are a combination of messages and handlers. Each step has a handler. Important to point out that it's not just one instance of that handler. It's actually many instances of these handlers spread across multiple machines. And it's the framework that takes care of the plumbing and making sure that the messages get to the right, not just the right type of handler, but the specific handler that is designated for that message. In order to foster competition in the ecosystem, the Open Teranode framework is intended to be a complete set of components and pipelines that will allow you to run a Bitcoin node. But it's architected in such a way that other people, third parties, can either build extensions to the network, to the Teranode, or they can even replace existing components and pipelines themselves. So the goal here is to foster competition among miners, because if they think they can do something better, more efficiently, they might build it themselves, run a custom version of their own Teranode, or they might license it to other people and earn some additional revenue that way. So here's an example pipeline. This is just the transaction validation pathway. It's not everything that has to happen in a Bitcoin node, but it's the process of receiving a new transaction, validating it, putting it into a block template so that it can be mined. And this pipeline is built on top of the framework, and it defines the workflow and the system logic. And of course, these pipelines can scale to meet real demand, because you can split a pipeline in two and run multiple ones in parallel. And here we've got an example where we're running a complete pipeline on each of the two cluster nodes, but we can actually break it up any way we want. We could break it down the middle so that one cluster node runs the first three of these pipeline steps and another runs the remaining three. How you distribute these workloads is just a question of configuration and optimization. So the basic functions of the Teranode framework are handling the message routing and the I/O layer. The I/O layer is pluggable, so you can swap it out for direct connections or use a Kafka message bus or whatever happens to suit you best. It contains a lot of tools for internal performance monitoring and generating feedback, so that when you're building a Teranode configuration, you can actually see inside. It's one of the more challenging things with a distributed system like this, being able to understand where bottlenecks are so that you can optimize by putting more resources in the right place. It contains a simple injection mechanism for binding external components. So you have an external component that is not integrated with the framework. You can easily connect those components in. A good example of this would be the Mappy. The Mappy component will receive transactions from users, and it wants to inject them into the Teranode framework. It also wants to find out what happened to those transactions. Did they get accepted, et cetera, so it can send a response back to the user. And we have an event registration and callback mechanism built into the framework to be able to handle that. So components, these are just some of the components that we're going to build, that we have built into the Open Framework. The components can be used in other contexts. One way we might do that is putting a UTXO appliance into the existing Bitcoin SV software to boost its capacity and give it a longer lifespan. And of course, the components are also able to be built by third parties as well. And this is an example of a third-party competitive implementation, I suppose. This is another part of the Teranode pipeline that handles block validation. An additional service that you might want to offer as a miner might be some kind of transaction indexing service and distribution service. So you might have paid subscribers, but an obvious place to plug that in is right after block validation. In fact, you might even want to rewrite the block validator yourself if you think you can build a more optimal version. So we're going to start taking a look at the Teranode itself now. And here we have, this is a video, the live bit's coming. Here we have the same pipeline that we just described earlier. And this is actually a live view on a dashboard. We expose a lot of metrics in the Teranode that can be displayed visually in this sort of dashboard format. And this is a simple version, but it's not actually the version that we're using today. This is a slightly more complex version. And in fact, it actually has two pathways for validating transactions. Transactions that have a relationship to each other can be validated in a much more optimal way if you know in advance that they have a relationship. And so down the bottom, you actually see the same pipeline that we were looking at before. And the top is another pipeline that is optimized to handle related transactions. And you can see over there on the right-hand side, there's a validate inputs handler. And they are both kind of branches of the pipeline join and connect to each other at this point. So let's actually take a look at a working live Teranode. This is a dashboard that we use for what we call ramp-up tests. When you put together a configuration, which is basically deciding what handlers run on what nodes and what pipelines you're actually using, we need a way to understand its capacity because no system has unlimited capacity. And if you start feeding more input into a system than it can handle, things will start to break down and go haywire. So you need to understand the capacity so that you can actually throttle the input at the entry point. And this dashboard here just shows us pipeline latency, and that is how long does it take from a transaction to get injected into the Teranode framework until it gets validated and put into a block template. And down the bottom here, we have a little more, a couple more gauges that show transaction submission rate and transaction validation rate. So I've just been running a Teranode in the background. That's what I started when I got onto the stage. And now we're actually going to try a real live ramp-up test. This is a deployment script. We've got 10 servers in a data center in Germany that we use for this sort of testing. And we're firing it up right now. And what we're actually looking for, it'll start to pop up in a second. We're looking for the point where latency starts to increase. That is, more messages are coming into the system than the system can actually handle. And so what happens is they start to build up in a queue. And you'll see the time it takes from when you send it into the system to when it pops out the other end will start to increase because they're sitting in this queue for a period of time before they even get to start. So we designated 100 milliseconds as the failure point. If latency goes over 100 milliseconds, we consider that to be the capacity of this configuration. And this ramp-up test is slowly increasing the rate of input. That's over here. We've got a rate limit about 20,000. And over here, we've got a graph of the same. The yellow is the actual rate that transactions are being validated, and the green is the rate that we're feeding them into the system. And you'll see that they hug each other pretty tightly. And OK, so right now, we've actually just crossed the fail threshold. Remember, this is 2 cluster nodes, or C nodes, we call them internally. So we can take this failure threshold, and we can see we've got around about 25,000 transactions per second. For reference, we don't think that the Bitcoin SV software would be able to handle a validation rate like that at this point in time. So you can see that the latency is just shooting up sky high now. That means that the system is overloaded. So we know that we can run this safely in the 20,000 transaction per second range. So let's test horizontal scalability. Now we're going to start exactly the same configuration, but we're going to do it using 4 nodes instead of 2. Now, this will actually create additional load on the system because whilst we break pipelines up in parallel, there are actually points where they have to talk to each other, and we call that cross-shard communication. So you don't expect to get perfect horizontal scalability because you will basically increase the amount of network throughput that is happening. This is an example. Here we go. Yeah, this is an example of the network usage under that particular configuration. So you can see that as it was ramping up, the network usage increased, and you can see that the CPU usage increased. This is pretty much the fail point when the CPU started to get saturated. So this one is creeping up. It's well and truly past the point where the 2-node configuration failed, and we're just about to cross the fail threshold right now. So let's take a look at where we got to. We are there. And we can see we've got about 50,000. So that's actually almost close to perfect, which is unusual. But I guess the demo gods are smiling on me today. This particular configuration isn't completely optimized. There are all sorts of optimizations that are still available to us because we've been focusing on the framework itself. We have run this across all 10 nodes, and I have actually seen volumes in excess of 100,000 per second. I wasn't quite brave enough to try that one today, live on stage. But there we have a real-life example of a Teranode that is able to scale. If I had more time, I would show you one that's actually running at a steady-state capacity and show that it actually can continue for a long period of time without any problems. So we've used some conservative numbers here. I'm assuming 10,000 transactions per second per cluster node. I'm assuming only 90% scaling capacity, scaling factor. But it shows that Teranode throughput is basically a function of how many cluster nodes that you configure. There's a little cost model using the current fee rate, assuming there's 100 miners running, or 100 mining pools rather, and assuming that they're supporting a 100,000 transaction per second throughput. That will give you an average block size of 30 gigabytes, assuming they're all payment transactions and not database data transactions. And it costs us, well, our clusters that we're using, they're bare metal servers, cost us about $1,000 USD a month. I've doubled that because you actually want to have excess capacity. But that equates to a revenue per miner, each one of these 100 miners, of about $1.3 million USD in transaction fees per month. So you can see these numbers are so far apart, there's plenty of margin for error there. And in fact, it shows that the Bitcoin transaction fees have huge capacity to come down. And that's assuming that we don't even optimize. So lastly, what's the rollout plan? Well, by the end of this month, we're hoping to actually have alpha versions of Teranode listening on the mainnet. They won't be trying to produce blocks. They'll just be listening and processing peer-to-peer messages. We'll also build, we have built scale testnets, global scale testnets for the Teranode specifically. We can't do this on the scaling testnet because we'll crush it. The throughputs that we saw there, even with 2 and 4 nodes, are probably enough to bring the STN to its knees. The next stage is for us to start producing block candidates and validating them against the Bitcoin SV software to ensure that we have protocol compatibility. This is critical because if we don't do that, then we have a risk of a chain split when we actually start to mine blocks against the Teranode. So we've had this capability built into Bitcoin for a couple of years now in anticipation of this testing moment. And the next stage, of course, is starting to try mining blocks on the mainnet. I would imagine that that is going to be a phase that will run for quite some time. And miners will run in a mode where they will fall back to Bitcoin SV in the event of an incompatibility incident. And eventually, the Bitcoin SV software itself will be retired. So that's it. I think I just wanted to make the final point that because we have proven that Teranode can scale, we've proven what what Satoshi always said about Bitcoin. Bitcoin can and does scale. Thank you very much.
Reimagine the world's financial system. One built on being simple and fair, not one that's overcomplicated, outdated, and broken, and keeps a quarter of the world's population from accessing it. Reimagine your own finances. Do you have full visibility and control of your assets and investments? We believe there's a better way, a new future for financial services. One built on equal opportunity, where possibilities are limitless, not limited, and everyone can live the life to which they aspire. At Fabric, we're weaving a better future of finance for the billions locked out and the billions locked in. A safe, open, and fully transparent financial ecosystem built on innovative technology, where anyone can transform, hold, trade, and grow their assets, all in one accessible place. But this journey isn't ours to take alone. Are you ready to join in? To reimagine a better future with us? Where everything is digital and anything is possible. Fabric. Reimagine prosperity.
Data is double-edged. Wield it well and build your place in tomorrow. But trust it blindly and risk watching your progress crumble. Because much of the data we rely upon isn't reliable at all. At nChain, we believe in data, but we put no faith in it. Instead, we build tools that enable enterprises to trust the data upon which they rely. nChain, data without question.
Is greatness really just for a chosen few? For prodigies? For superstars? It's not planned. It's experienced by those with great support and some resilience. For those that strive to go to the edge once more, pushed and guided with excellent support. Support that provides groundbreaking technology by and for those that know it's all about velocity.
Imagine in 1997 paying for something with your watch. Remember the last time you used cash? The world has been digitized. Almost.
Cash was once seen as the last bastion for reform, but now is on the decline. Digital transactions have outcompeted hard currency since 2017 in the UK, but breakthrough bold technologies like blockchain have revolutionized more than just money.
Disruptive technologies call for disruptive lawyers, ones that don't just accept the trend, but find new ways of interpreting the law. We are currently the only global law firm with a real track record in the area of Bitcoin and blockchain. We are results driven and care only about securing the best possible result for our clients.
We trace the supposedly untraceable. We pioneer the future of law. We deliver new solutions. We are law changers.
The biggest sickness in healthcare isn't a disease. It's not a bacteria or a virus. It's the silence. See, the data we need to combat diseases, to stop suffering, it's not waiting to be uncovered. It's stuck behind closed doors in stubborn silos. The healthcare industry has the data to improve our lives in untold ways, but no one communicates. And in that silence, countless lives are lost. That's why at EHR Data, we're building the largest ever shared data set of human health. And it won't belong to a hospital, government, a corporation. It will belong to the rightful owner of your healthcare data, you. We're merging healthcare records with blockchain to finally put you in control. Because your data doesn't belong on private servers. It should be in your hands in service to your health. The greatest sickness may be silence, but the silence stops when you have a voice. EHR Data. Own your health.
Different backgrounds, diverse geographies, and disparate experiences can all inspire ideas that lead to breakthroughs. And with blockchain, we've barely scratched the surface on its potential. So what's next for this breakthrough technology, and where can it take us? That's where you come in. Learn to leverage your creativity and harness the power of blockchain technology to tackle the biggest challenges of today and opportunities of tomorrow. Discover how you can make your ideas a reality with BSV, the only blockchain that scales unbounded, offers a stable platform with world-class security, and the support of a global community of experienced, knowledgeable developers. Join the 4th BSV Virtual Hackathon, and let's build the future on the blockchain.